Welcome to this explainer. Today we're uncovering how Network Address Translation, or NAT, executed a massive rescue mission to literally save the internet from collapsing under its own explosive growth. If you've ever wondered how we connect billions of modern devices using a system designed for just a fraction of that number, well, you're in exactly the right place. Here's our roadmap for today. We're going to start by looking at the IPv4 scalability crisis, move into CIDR and private addressing, break down core NAT concepts, and compare static and dynamic NAT. Then we'll explore overloading with PAT, and finally wrap things up with some real-world configuration and troubleshooting. Okay, part 1, the IPv4 scalability crisis. We were quickly running out of room. 0. That's the exact number of IPv4 addresses we would have had left by the mid-1990s. See, the original design of the internet required every single organization to get unique registered classful network numbers, and the admins had one strict rule. Absolutely no IP addresses could be reused anywhere, period. Now, that meant routing worked flawlessly because every address was globally unique, but with the sudden explosion of the internet, we were chewing through that address space at a terrifying rate. Without a major pivot, internet growth would have literally just hit a brick wall and stopped. Moving on to part 2, CIDR and private addressing. These were the crucial stopgap measures. So, before a permanent fix was finalized, the industry had to deploy a couple of emergency stopgaps just to give us some breathing room. First, they rolled out CIDR, classless inter-domain routing, to manage routing efficiency and shrink the size of internet routing tables. Right alongside that came private addressing, defined in RFC 1918. Now, this was a huge deal. It allowed companies to reuse specific IP ranges internally without causing routing conflicts out on the public internet. But there was a catch, a pretty big one. Those private IP addresses, they couldn't directly traverse the public internet at all. Which brings us to part 3, network address translation concepts. The hero finally arrives. So, how do those private addresses actually talk to the outside world? Enter the NAT router. It acts as a gateway right at your network edge, intercepting internal packets. As a packet leaves your private network, the NAT device strips away your private IP and translates it to a smaller pool of public IPs on its way out. It keeps a careful record of this switch in a translation table. Then, when the internet sends traffic back, the router checks that table, flips the public IP back to your private one, and forwards it straight to your computer. It's this brilliant middleman operation that also happens to hide your internal network architecture from the outside world. A nice little security bonus, right? To really understand those translation tables, you've absolutely got to master these two critical vocabulary terms. Inside local, that's your private address, the one configured locally on your laptop or server. Meanwhile, the inside global address is the publicly registered internet-facing IP that the outside world actually sees. Trust me, knowing the difference between local and global in a NAT configuration is absolutely essential. All right, part 4, static and dynamic NAT. Let's look at the early variations. First up, we have static NAT. This provides a strict one-to-one mapping between an internal inside local address and an external inside global address. While this securely hides your internal numbering scheme behind the router, it kind of completely defeats the goal of conserving addresses. Why? Because you still need a legally registered public IP for every single internal user. Basically, an admin has to manually configure a specific local IP to perfectly match a specific global IP. Not exactly scalable. Dynamic NAT improves on this, but only slightly. It lets admins configure a shared pool of registered addresses. The idea here was that since not everyone in the company browses the web at the exact same time, they can just check out a public IP from the pool when they need it and return it when they're done. But let's be real. In today's networks, pretty much every device needs continuous internet access, right? Since it still relies on a one-to-one connection while active, dynamic NAT just doesn't drastically reduce overall IP consumption. So we needed something better. Part 5, overloading NAT with PAT, the ultimate solution. Now here is the real aha moment of this technology. By appending a 16-bit transport layer port number to the IP address, PAT acts exactly like a corporate mailroom. Think about it. An entire corporate building uses just one public street address, while the internal mailroom uses desk numbers to sort the mail to individual employees. PAT does exactly this. It translates the private IP addresses and TCP or UDP flows into a single public address, paired with a unique port number. When you compare them side by side, it's super obvious why PAT is the most popular form of NAT. Static NAT is this rigid one-to-one setup that just eats up your public IP space. PAT, which is known in the Cisco world as NAT overload, is a many-to-one mapping. And just how efficient is this? Well, because the port number field on a packet is 16 bits long, translating those transport layer ports scales incredibly well. You can theoretically squeeze up to 65,000 internal hosts onto just one single public IP address. Now that is a total game changer.
Finally, Part 6, Configuration and Troubleshooting. Time to actually apply this knowledge.
When you're setting this up in the command line interface, remember that PAT requires one magic word: overload. Whether you're translating to a dynamic pool or directly to a router's outside interface, if you forget this single word at the end of your syntax, your router's going to attempt standard dynamic NAT, and you'll exhaust your IP pool in seconds. So whatever you do, don't forget the overload keyword. Okay, but what if your translations just aren't working? Well, follow this logical playbook. First, ensure your pools aren't completely empty. Second, check your access control list logic. NOT relies heavily on ACLs to identify which private IPs are allowed to be translated. If your ACL is misconfigured, no packets get picked up. Simple as that. And third, verify you haven't accidentally flipped your interfaces. You absolutely have to declare which interface is IP NAT inside and which is IP NAT outside for the traffic to flow properly. To actually execute that troubleshooting workflow, rely on your show and debug commands. Show IP NAT translations is great because it lets you look right into the brain of the router to see the exact port and IP address mappings happening in real time. Show IP NAT statistics gives you the big picture on how heavily your pools are being utilized. And if you really need to get into the weeds, debug IP NAT will output the active translations directly to your console as the packets pass through. As you wrap up your prep, I want to leave you with this final thought. Considering PAT can squeeze up to 65,000 internal hosts onto a single public IP, just how long can this brilliant mailroom trick truly delay the inevitable worldwide migration to IPv6? It's an incredible piece of tech that has kept the internet scalable for decades, but with the massive explosion of modern networking, it's a critical question to ponder. Thanks for joining me for this explainer on network address translation.